So now that we understand what we mean by the idea of motion, we need to actually find ways of how to describe motion. So in order to describe motion, we can do it in two ways. We can either use graphs or we can use equations. Now the graph section that we're going to do now is not complicated, but you actually need to pay attention and you need to make sure that you understand what is happening in each type of graph. You have to understand this 100% because we're going to take these graphs all the way up to grade 12. So if you're intending on taking physical science all the way, you need to know how to use these graphs. You need to know how to do two things. The first thing you need to know is you need to know how to draw the graph. The second thing you need to know is how to explain the graph. And then another thing would be to interpret the graph. All right, so the graphs will always look the same, right? But how we describe the motion, that's important. And what we mean by motion, we can have the motion of a car or a person or a ball or whatever the situation is. We want to know what does its motion look like if I am going to use a graph or if I'm going to use an equation. So when we do the graphs, it has a lot to do with graphics, but when we do equations, it's a lot of calculations. So very important section. So let's look at this first setup here. As we can see, we have a man here and he's moving. And we want to take this man's motion and put it onto a set of axes, like a graph. So there are three types of things we're going to look at. We're going to look at delta x, which is your displacement over time. We're going to look at velocity, delta x, and we're going to look at velocity over a time period. And then we're going to look at acceleration, also over time, and what that would look like in a graphical situation. So these are all the vectors that you've learned about, or the vector quantities that you've learned about in your previous graphs. And now we're going to look at motion. So if I'm looking at what this person's doing, they're just walking in a straight line. And when they're walking in a straight line, it will be useful for us to do a displacement versus time graph. So let's have a look at the first type of graph. So the graph that we're looking at is what we call a displacement versus time graph. Now, when we talk displacement versus time, or when you see it in this kind of a setup, if I'm looking here versus, when we say displacement versus time, it means whatever comes first in this diagram is your dependent variable. Right? So I know that this one must go on the y-axis. Time will become my independent variable. And it has to be, because time is a scalar and can only move in one direction. So that's going to be on the x-axis. So the first thing I need to do is I need to go to my graph and I need to fill in the information, and I've got to say that this is displacement, and I must put my SI units. So I know that displacement is measured in meters. Then I go here to my x-axis and I say that this is time and this is going to be in seconds. So when I'm looking at a displacement time graph, I need to understand how do I describe someone's motion in terms of a graph. So let's look at a couple of things. The first thing is, in a displacement time graph, the slope or the gradient rather, of a displacement time graph will always measure the velocity in meters per second. So that's how fast or how slow someone is moving. So when I look at the gradient, that's what it's going to measure, right? Different gradients. So when the gradient changes or different changes in the gradient mean different things. So for example, let's say you're moving in a straight line. Let's say you're going from your house, you're going to the mall or wherever, all right? The first thing that we need to look at is, on my y-axis, this is how far I am, all right? And the x-axis is how long. So how much time is it taking me to do all of this stuff? At point 0, 0, that's the next thing. At the origin, at point 0, 0, that is the start position. Now, if that's where you start from home, and we're going to call that a frame of reference, right? You know that you can never go past the frame of reference. Because if you go past the frame of reference, you're going into the negatives. So what that means is, because we can't go past the negative value, we know that in a displacement versus time graph, we are never going to have, there's going to be no negative distance. That means on the y-axis can never be a negative. Never, ever, ever, ever. Because you can't go backwards, if that makes any sense. You can't go past your frame of reference. Right, so let's have a look here at this graph. Sorry. All right. Now when I'm looking at this type of graph, let's say I start at my house, starting here at my house, and let's say I start walking towards the mall. All right, so I'm walking towards the mall. So I start off slowly, and then I start walking towards the mall. And let's say there, that's the mall. All right, so now I've gone from looking at this situation that I have in front of me here. I need to look at what's happening in my actual graph. What does this gradient actually tell me? Let's look at 2 points here. Let's look from 0 to about 2 seconds. What we notice about the slope is that I have here a curved slope. Now, when I have a curved slope, that's telling me that, now remember, the gradient is describing velocity. So everything that I talk about with the gradient has to deal with speed. How fast am I going? How slow am I going? So if I see a curve here, that means I am accelerating. I am, what we say, remember what we said was accelerating? We're speeding up. That's why I'm seeing a curve. Right, the next thing that I look at, let's say from 2 seconds here to 9 seconds there. This little zone over here. What I'll notice about that area is that area is not curving. And what it actually should be doing is it should have a straight line like this. Okay. Now, what does that straight line mean about my speed? So if I'm looking here at this kind of a curve here, right? This means that I have something we call uniform motion. So if I see an upward or downward slope, then I'm looking at uniform motion. That means I'm moving at a constant speed. Right. When I'm moving at a constant speed, right, I'm allowed to use these upward and downward slopes. If I choose an upward slope, so a slope that goes like this, then I am moving away from the frame of reference. If the slope goes downwards like that, I'm moving towards the frame of reference. So if my slope is going away from this 0.00, which remember what I said about 0.00, that's that's going to be where you start. So now I'm moving away from my house. I went from 2 seconds here to about 8 seconds here. And in this area, I went away from my house. So in terms of frame of reference here at this point, so let's say this is A, B, C. Between B and C, I moved away from my house. So now I'm at point C over here, I am 9 meters away from home. All right. So let's say that's where the mall is. And I get to the mall and I decide that I'm going to stay at the mall for some time. All right. So now I'm staying at the mall. I need to represent that. I'm not moving anyway, just at the mall for a little bit. So if I have a look now, oops, just do that. Right. What you'll notice now is that from point C to point D, it's a flat slope. When I see a flat slope, it means there is no movement. That means whatever's happening between C and D, the person is stationary. Or I can even say at rest. They're not going anywhere. They're not moving. All right? So understanding these slopes, curved slopes means I'm accelerating. A straight slope means I'm moving at uniform or constant speed. All right? Downwards and upward slopes are moving away. So now I'm at the mall and I'm staying at the mall for a certain period of time. So between C and D, I'm not doing anything. I'm just at the mall. Then what needs to happen? I need to go home. So let's say my mom phones me now and she's like, listen, you need to be at home now. So I can't waste any time. So I gotta get home and I gotta get home as quick as possible. So let's have a look here. I'm gonna go from point D, I'm gonna go in a downward slope. And when I have that downward slope, I'm going that way, isn't it? So this is point E. Now at point E, now look at point E and point 00. At point 00 and at point E, I'm at the same place. So what we need to understand is that when I come close to the x-axis, I am moving towards the frame of reference. And that's what's happening here. Now look at the two gradients. The gradient of CB, all right, so the gradient of CB, let's have a look here. If I'm looking at the gradient of CB versus the gradient of DE, let's have a look at those two gradients. Just going to keep that up there. All right. Oops. When we look at different types of gradients, we need to understand what's the gradient actually telling me. So when the gradient, and I'm going to put it in blue, looks like that, right in the middle, that means I have a constant velocity, right? But my speed, my speed in this situation is what I would say is gradual. Gradual means you're not moving too fast, you're not moving too slow. So you're moving at an even kind of pace. If I take my gradient and I move my gradient closer to the y-axis, let's look at the steepness. Right, now I got a new gradient, and this gradient is very, very close to this y-axis. Now, when something moves closer to the y-axis, we say there is still you're moving at a constant velocity. That means your velocity is the same all the time. See, the velocity here, every second, we're moving up. I'm moving every second. Right, I still have a constant velocity, but my gradient looks a little bit different. It's steeper. So when I have a steeper gradient, what that means is I'm moving very fast. So how do I know that? If the gradient comes close to the y-axis, it means that you're moving at a constant velocity, but at the exact same time of moving at a constant velocity, you're also walking very, very fast. All right, if I look at another type of gradient, let's say I take that same gradient, and let's say I come and I draw the same gradient, the same slope, but now my gradient looks a little bit more different. Right, so now when my gradient looks like this, can you see that the gradient is moving towards the x-axis? So when it does that and it moves closer to the x-axis, I've got a gentle slope. And when I have a gentle slope, it means that I'm moving slowly, but still at a constant velocity. Right? So when I'm looking at the distance versus time graph, I'm looking at a situation of how do I describe this motion? And I can see it again here. Let's say if I use, for example, I use the DE situation. The DE slope that I'm looking at looks a bit different. And this DE slope looks a little bit different because, so look here. Sorry. If I look at the first one, the BC slope that I have, that BC slope looks like this. It looks like a normal gradual slope, which means I'm moving at a very average kind of pace. So this would be the BC one. But when I look at the DE one, the DE one looks a little bit more like this. Oops. I've got my DE slope here. So look here. When this DE slope comes, it's much steeper because it's close to the y-axis. So if I had to sketch that, what I'm trying to show you is that when I'm coming straight from here to here, that's gradual. When I'm coming straight from here to here, so that's gradual. When I'm coming from here to here, can you see I've gone closer to the y-axis? That means I'm moving fast. And if I had to draw a line that went like this dotted line, that would mean that I'm moving slow. So both of these types of graphs, this is just a rough sketch, but you can draw it neatly, or you should draw it neatly, because you're obviously learning this for the first time. So what we can do is we can use steepness to determine how fast or slow a person is moving when they're moving at a constant. So this works for constant velocity. Right? Another way of looking at a displacement time graph, I'll just move this up, is you can look at displacement or we're going to use displacement time graphs. You can look at it like this. So let's say I had this graph here in front of me. That's the graph they've given us. And now from that graph, they want us to explain what is going on. Right, let's have a look. Right, the first thing that I can see here is at this initial stage here. At this point, please make sure you get these graphs into your books. I've got an increasing slope. And if I have an increasing slope or curve slope, it means I have an increasing velocity, which means that the velocity is not constant. And when the velocity is not constant, I have acceleration. Right, that's great. Then I'll notice that point from about there to there, in that little section over there, can you see that I've got myself a bit of a straight line? So what's happening there is I've got a constant or a gradual slope. And when I have a gradual slope, it means the velocity is constant. Right. Now, if I'm looking at axes, I know that if I'm just looking at this diagram above, if I'm moving along the axes, I'm moving in what we call a positive direction, or I have a positive velocity. It's increasing all the time. Right. Then if I look here, from let's say here to here, have a look at the shape of the curve. It starts off straight and then it starts to bend. Right. Now when we see that bend happening here, what I've got here is a decreasing slope. And when I have a decreasing slope, it means I have a decreasing velocity. Now, if something has a decreasing velocity and it's a curve, it means I've got acceleration. But now, because this one here was speed up, this one's doing a different thing. Can you see? This one was a bit under. This one's going over. So instead of acceleration, I've got acceleration in the negative direction. In other words, I am slowing down. All right. And if I'm slowing down, it means I've got deceleration. So either you can say it's acceleration in the negative direction, or you can say it's deceleration, but it means the same thing. You're slowing down. Right. Then if I look here at this graph, I reach a little bit of a peak. So at this peak point here. At this peak point, I know that nothing is happening. It's called a horizontal point. And at a horizontal point, it means the slope, the slope is 0. And if the slope is 0, it means there's a velocity of 0. And we said if something has a velocity of 0, it can either be called stationary, or we can say it's at rest. There's no movement at that point. Right? Then we look at this next little slope here. Here's another bright color. Right, if I look at this slope over here, look what's happening here. When you stop somewhere and you start moving again, you start to increase, isn't it? And so I've got this situation here, and I've got myself a negative slope. So I'm just going to put it here somewhere. I've got a negative slope, and this negative slope means I still have speed, but I have a negative velocity. So now my speed's going in the opposite direction. Have a look at what's happening here. Have a look at this curve area here. What's happening here is that my curve is becoming flat. Oops. And if the curve becomes flat, it means that what's happening now is that your velocity is becoming less. So velocity is less negative. Sorry, no, you can't see that properly. All right, but my object now, so at some point, if I'm looking at my object started there at point A and moved away from home to a certain point. So it moved away, and then it started to come back home, isn't it? All right, so there's one last part, the last little part of your graph. Sorry, let me just get this black back. Is over here. What's happening there? So if I see my curve, can I see it's a flat line? If the curve has a flat line, it means, and I'm just going to put this information, you'll obviously put it in the right place in your book. It means we are continuing to zero. It means there is no movement. Right? When I see a flat slope, it means the object, whatever was moving, is at rest. So when I have these types of graphs, it's useful to understand that either the graph is going to look like this graph at the top, or the graph is going to look like this graph at the bottom. The only graph that's going to have curves on the graph is a displacement time graph. So if ever I have a displacement time graph, I need to make sure I'm looking at the curves. Because when I see curves, because they're going to ask you, here's a graph, write a heading for the graph. Now, if you don't know what's happening on the graph itself, you're not going to be able to do that. So if I think about this first graph, or let's look at the first graph. You started off here at 0, 0 at home, and then you started accelerating. So you started speeding up. Then from point B to point C, you moved at a uniform or constant speed. Then you got to your destination and you spent a bit of time. So look, you started here at point A, 8 seconds, and you left the mall at 14 seconds. So you spent some time there not moving. Afterwards, your mother phoned you and told you need to come home quickly. So you ran home. So can you see how steep that gradient is? It's coming closer and closer. If the gradient was out here somewhere, it means you took your time to get home. If the gradient was down here somewhere, it means you literally jumped from the mall into your house. Right? It didn't take you any time. In the same time period, can you see? At 14 seconds, you were at the mall. Next thing, at 14 seconds, you were back home. Not possible, but, you know. So the closer you move to the y-axis, the faster you're moving. The further you move, then you're moving slow. Right, so you got home after 17 seconds. Right, if I look at this other graph that we were looking at here, again, you've got a displacement. Sorry, just move this. You've got a displacement time graph. And when you have a displacement time graph, you can look at it in a different way as well. You can look at things moving in a more rounder way. Right? When we look at displacement time graphs, you'll notice about these types of graphs is that when we have a positive slope, so in moving, let's think about it like this. A positive slope, if you have a positive slope, you are increasing velocity, you're moving in the positive direction. A negative slope means you're moving in the negative direction, and a zero slope means you're moving at a constant velocity. Right? Then the other thing that we look at is, one of the other things we looked at was something we call instantaneous speed. So when we think of instantaneous speed, so there's two things happening here on this graph. The first thing is you're telling me, here I went about, here at the beginning between A and B, I started speeding up. Between B and C, I was walking at maybe 4 meters per second, or whatever the case is. D to C, I was moving at 0 meters. So let's say from here to here, you were walking at 1 meter per second. That's very fast, right? Here you're moving at 0 meters per second. You didn't move. Here you were moving at 2 meters per second because, you know, your mom was going to give you a beating if you didn't get home on time. So when we talk about instantaneous speed, so if we remember instantaneous speed, if I'm looking at a graph and I've got this kind of a setup, right? Instantaneous speed is, let's say I was looking at that curve section. What was my exact speed at 0.5 seconds? What was the speed? Right? So what I'd have to do is I'd have to look at distance here, or the displacement here. And I could say that the velocity is equal to the displacement over the change in time. So if I look here, I can use this formula to find instantaneous speed, as in how fast was I moving at that exact moment. You can use these formulas because you've got displacement, you've got time, and remember that's what the graph is measuring. So I know that a displacement versus time graph is going to be looking at velocity, but velocity is also displacement, all over change in time. So I'm allowed to use this formula with this kind of a graph. So this brings us to the end now of a displacement versus time graph. So with the displacement versus time graph, we can look at some information here. All the information I've summarized for you here. I'll just put this in. Please make sure you get this information also into your books. It's a summary of everything that we've just done now. All right, so we can say is, on a displacement time graph, we know the slope equals the velocity. I'm going to put this in pink. The velocity in meters per second. We know displacement is delta x versus time, which is in seconds. The y-intercept equals the initial displacement. So when I'm looking at the y-intercept, I must be looking at 0, 0. At 0, 0, that is where I start. If I go away from 0, 0, I've got a positive displacement. If I come towards 0, 0, I've got a negative displacement. I'm coming back home. When we talk about when the two curves coincide, sometimes you could have the situation. Let's say they ask you to sketch a graph of you and your friend. You at your house, your friend is at his house, right? And both of you leave together. Okay, let's do this. Let's say it's your mom and your dad. They both leave home at the same time. There's your mom, she's going to work. There's your dad, he's going to work. Then after some time, obviously the day is over. Your dad's been at work the whole day. Your mom's been at work the whole day. Now they're going to come home. But on their way back from work, they decide you got into a fight at school, so now they have to go to school to meet up with you because you're in trouble with the principal. So your father goes towards school, and your mom, she was at work, she also decides to go towards school. and then they meet at school. So can you see this point here where the two graphs are intersecting with each other? That means they at the same displacement at the exact same time. So if I look at my displacement, look, there we go. So see where their displacement is. Let's say they are 750 meters away from home. But that 750 meters away from home, that's your school. And now they're both at that school. So if two curves coincide, it means they're at the same place at the same time. Straight lines mean constant velocity. Curved lines means acceleration. If it's going under constant acceleration, we can have in terms of parabolas. So for this type of graph, please, you need to know your formula for your parabola. You need to know how to get the formula. You need to know the turning point. You need to know x-intercepts. All right, so please make sure that your math, this is why you have to be good at maths to do this object. Instantaneous velocity is the slope of the line tangent to the curve at any point. So remember what I said? Tangent, it must cross. There must be a crossing point. So if I wanted to know what was your father's speed at this moment, I can draw a tangent like this. And that will tell me exactly what his speed was when he left work after you got into a fight. He must have been speeding. Right, positive slope means motion in the positive direction. So positive slopes always go upwards and away. Or away. Negative slopes means a negative direction. It always goes downwards and towards the frame of reference. A zero slope implies it is at rest, or we can say stationary, or we can say a zero velocity, which means it's at 0 meters per second, right? And then the area underneath the graph is meaningless. It means nothing. So that means this zone over here for this kind of graph means nothing. We can get nothing out from the underneath of any type of graph. So those are the rules for the displacement time graph. The next thing we're going to look at is we're going to look at the velocity time graph. Very, very important. Each graph has their own set of slopes, their own gradients, their own meanings, their own styles. You cannot mix the graphs up because you're going to see the velocity time graph that comes up next. And that looks the same but means something totally different. So please make sure you absorb all of this before you go to the next one. Another way that we can look at this kind of graph is if I look at it like this. You can add this to your notes as well, right, for distance time graphs. Okay, the next kind of graph we're looking at is a velocity in meters per second versus time graph. Right, now in a velocity versus time graph, I know that again, if I'm looking at a velocity time graph, the variable that comes first is my dependent variable, and that's going to go on my y-axis. Right, time is always independent. How am I spelling this word? Independent variable, and I will label that on the x-axis of my graph. Right, the next thing when I'm looking at this is the slope or the gradient. This is going to give me the acceleration of the graph in meters per second squared. Right? When we look at these types of graphs, again, if I have straight lines, I'm going to have, if I see a straight line, it means I have constant acceleration. That means I'm constantly speeding up. If I have curved lines, I've got non-uniform, right? Then when we looking at these sort of slopes, remember what we said? The slope goes upwards like this, then I've got a positive acceleration. Moves downwards, I've got a negative acceleration, or I'm decelerating, right? If I have a zero slope, I'm going to show you that now. It means I am not accelerating. That means I'm moving at a constant velocity. And I know zero slopes are flat. Alright, so let's have a look at how this graph looks. Let's say you leave your house. So the scenario is a little bit different now. Let's say you leave your house and you're going to school. Now, because you just left your house, you need to start speeding up. So you left your house and you start speeding up. So it's a little bit of an acceleration. Right, so we're going from 0, 0 from point A here to point B. Right, then you realize that after you were in the suburbs, you actually needed to start getting onto the highway. Let's reduce this. So you're going to start moving onto the highway, which means you need to accelerate a little bit more. So you might have started at 0 meters per second, but now you ended up from point A to point B, you ended up at 50 kilometers per hour. But now you're getting onto the highway, right? So you accelerate and accelerate and accelerate until you get onto the highway. Right, now you're on the highway. So you're on the highway and you get to the optimal speed on the highway. So the speed on the highway, say that's point C. Oops. Right, that's point C. On the highway, you're at a constant velocity. So you're at constant velocity. Remember what we said about constant velocities? It's a flat slope. Then let's say you forgot something at home. So now you need to come to a stop quickly so that you can do a little bit of a U-turn. All right, so you're gonna, oops. Now it's a quick stop because it was an emergency situation. So you're gonna stop quickly. All right, now you're there at that point. Oops. You're there at point E. Now, at this point, you've stopped for a few seconds. Let's use another color. Let's use red. You stop for a little while. And now you're at point F over there. Then you decided you need to go in the opposite direction. So you start to speed up a little bit. All right, but remember, you just stopped. So you're going to accelerate a little bit. Oops. But now after doing this whole thing, accelerate it for a little bit to point, oops, what have I done there? You accelerate it a little bit because you got to go back, E, F, G. And then what happens is, as you're going back home, you're at a steady speed again. Please make sure your graph goes a bit longer than my graph. And then you're at point H over here. Okay, so let's just talk about what's happening in this graph. If from point A to point B, notice about the slope. It's a very, it's a gentle slope. So it looks a little bit like the acceleration versus time graph. I mean the distance versus time graph, but they are different things. The slopes look all the same, but it's telling me a different bit of information. Don't forget that this is velocity in meters per second, and then this here will be time in seconds. Right, so from A to B, I've got this gentle slope. So I know that what that means is I've got acceleration, because remember, that's what this graph is telling me. I've got acceleration, so it accelerates slowly. Right, then from B to C here, can you see that the slope, there's a gradual slope. So now I have a situation where I'm accelerating quicker. Right, then at point C to D, can you see it's flat? In this graph, it doesn't mean that you stopped. In this graph, it means you're moving at a steady speed, or we can say a uniform speed, or constant speed. You're not increasing or decreasing. You're staying at the exact same speed. So if I look here, it says here a zero slope means you're not accelerating. You're just moving at a constant speed. Then we look here at from D to E. Have a look at the slope. The slope is a steep slope, but look at the direction of the slope. This slope is going down, so it's a negative slope. Right? And if I have a negative slope, I mean I'm slowing down. And if I'm slowing down, I've got deceleration. And if I look at the steepness of it, I can say it's a very rapid deceleration. Right. Then at point F, can you see point F? This point means something else when it reaches the x-axis here. Right? So at point F over here, when a velocity time graph reaches the x-axis, it means you have stopped. So that means no movement or stationary. And remember what we say. If I have uniform speed or constant speed, right, my acceleration, my A value there is equal to 0 meters per second squared. And if I've stopped, my A value is also equal to 0 meters per second, because I'm not going anywhere. So what you need to understand by this type of graph is when it returns to the x-axis, it's not the same as the displacement time graph, because what we say with the displacement time graph, when it comes back to the x-axis, you're back where you started. No. These ones, when you come back to the x-axis, it means you are not moving anymore. We can say it is at rest. Alright? If I look at G now, F to G there. F to G, if we look at F to G and A to B, they're kind of the same, except they're on two different sides. So if I look at where G is on the negative side of the graph. Then if it's on the negative side from F to G, I'm just going to put it up here. If F to G is on the negative side of the graph, it means, and you look at the slope, I still have a gentle slope, right? I have now a negative slope, and that tells me I'm going in the opposite direction. All right, but look at the kind of the slope. It's still a gentle slope, which means I'm still going to be, I'm just going to make this a bit smaller, accelerating slowly, but in the opposite direction. So that's what that means. Then if I look at H G to H is doing the exact same thing as C to D. It's a constant speed or steady speed. Right? Here in this situation, it's increasing as well. But look here, it's on the negative part of the graph. What we mean by negative is, look here, it's on the y-axis. When I line it up, it's on the negative part. The minute I see my graph going to the negative part of the graph, that means I'm going in the opposite direction. That's how that works. So if you're in the top half of the graph, in the positive y-axis, so look here, we've got the positive y-axis, and over here we've got the negative y-axis. If you're in the negative y-axis, you're going in the opposite direction. And if you're in the positive y direction, you're going in the direction of motion. Remember, we discussed that as well. So this is basically what your velocity versus time graph looks like. You don't have to go all the way here when you draw yours, though. You can go up to about 6, that's fine, 5 or 6. But usually how we draw this graph is we use a positive axis and a positive axis and a negative axis, because in these types of graphs, your speed, your acceleration can change directions. I can slow down or whatever the case is, right? So let's say they give you a graph and they give you a velocity time graph, and they ask you not to analyze it, but just to have a look at what's actually going on. Okay, so I'm just going to do this and bring this velocity time graph down here. Please make sure you get this into your books, because we're obviously going to do what we did in the previous one. We're going to add notes to it. Right. So like I said before, with the velocity time graph, is that it measures acceleration. So when I see this slope here, let's look at the first slope. It's going from point A here, let's say B, C, D, E, and F. And I see a G there. Right. When it goes from A to B, what I can see is that the first thing I've got is a positive slope. So this person starts off accelerating. So I can say there's a positive acceleration. Oops. I have a positive acceleration. All right, then what happens? From B to C, over here, I have a horizontal slope. So that tells me that the slope is flat. And if the slope is flat, if it's flat and above the x-axis, so if it's flat and above the x-axis, that means it's a constant speed or velocity. Constant speed or velocity. If it's flat and on the x-axis, then it has stopped. So there's another way of looking at that. Then from C to D, right? What happens from C to D and then D to E? From C to D, if I'm looking at this graph, from C to D, I've got a slope, a gentle slope, but a negative gradual slope. A negative gradual slope. Alright, so I've got technically a negative Right, then from D to E keeps going. So it goes all the way from C down to D, all the way to E. Right, so it's all in the same line. So what we can say here, if I have this negative gradient or negative slope, it means I have a negative acceleration. And if I have a negative acceleration, it means I am moving in the opposite direction. Right. Then if I look here on this end here, from point E to F here, we can see that little zone. I've got in the opposite direction an increase in acceleration, because I've got myself a positive slope, but my direction is in the opposite direction. So here I could be even slowing down. Then we got the last little bit there, and the last bit is from F to G in this little zone here. And because it's on the line and I said it's flat, it means it is stationary or at rest. No movement, because look, it's on the x-axis and it's flat. So if it's on the x-axis and it's flat, we said here above here, the object is not moving for that period of time. And that's what it looks like when we do a velocity time graph. Right, and then the last thing that we need to discuss here, if I have a look at this graph, and I look at this zone here, you see this that I'm coloring in, that's what we call, I'll put it in black so that it doesn't stress us out too much, we call that the area under the graph. Area, this is important. Now if I look at this graph, when we talk about the area underneath the graph of a velocity time graph, we are looking at the distance. If I can calculate the area underneath the graph, I will find the distance that this person has traveled. Now what's nice about these graphs is that you'll see shapes that we recognize. So let's look at the first little zone here and have a look at what shape that is. That's a triangle. The next shape is a rectangle. The next shape is again a triangle. Now by recognizing that, that means that if I had to work out the area underneath the graph, I could use from grade 9, I could use areas or area formulas. Oops. What am I doing? From grade 9. So common shapes you're definitely going to get are triangles. And I know triangles, A is equal to half times base times height. You can get squares or you can get rectangles. And I know that my area formula is length times breadth. What was that? Right. So, and my answer must be in meters squared. Right. So when I'm looking at this type of graph, and I've drawn up my graph, I can just go and have a look. So let's look at the first one. How would I know that that's the area? So let's say I wanted to work out the area of the first half from A to D. What was the distance traveled from A to D? Right, the first thing I'm going to look at is, I'm going to look here. I need the base and I need the height. My base is from 0 here to that point over there. Now that point's just before 5. So let's just have a look here. So for my first triangle, I know it's going to be half times base, area is equal to half base height. My base there is over here, and we can assume, let's say, that's 4 units. And my height is up here. That distance there is my height, and that's sitting at 15. So I've got half times 4 times 15. Right, and that gives me 30 meters squared. Right, that's the first thing. The next thing I've got here is I have a rectangle. So here's my rectangle here. I'm outlining it. Right, the rectangle I know starts here at 4, but it ends over here somewhere. Right, so we're going to find out what that is. So if I'm looking at 5 to 10, this 4 over here, this line over here is at about 6.5. So if I take 6.5 minus 4, I'm going to end up with 2.5. So I know that for the rectangle, I know that the length is 2.5, but I know that the breadth is still 15, because look, the breadth still goes up here to the top, and it lines up there. Can we see that? All right, so I'm going to go area is equal to length times breadth, and it's going to be 15, 2.5 multiplied by 15, and I'm going to get 37.5 meters squared. Right, so I've got that so far. Right, then I've got my last triangle. My last triangle is going from 6.5. Let's see if I can use another color. It's going from 6.5 over here to 15. All right, so if I'm looking at that, 15 minus 6.5, and I'm going to get 8.5. So the distance between this point and this point is 8.5. But look at the height. The height is still at 15. All right, so I've got a triangle here. I've got a base here of 8.5. I've got a height here of still 15. And area is equal to half base height, which is half times 8.5 multiplied by 15. That gives me 633.75 meters. All right, so now if I want the distance from A to D, I can say 30 meters squared plus 37.5 meters squared plus 63.75 meters squared. And that gives me 131.25 meters is the distance that the object or the person traveled. Right, does that make sense? So how you break it up is you need to look at area formulas for triangles and area formulas for squares and rectangles. Right, and then the last part over there is a little bit of a summary of everything that has to do with your velocity time graph. Oops. Please make sure that you get this into your books. It's all the notes that's related to what we are up to right now. I'm just going to go through it with you. There we go. Here we go. Just do this. Right. On a velocity time graph, we know that the slope equals acceleration. So that's going to give us that, and that's the gradient. Don't forget, in these situations, when we talk about gradient, we talk about gradient of a normal graph. And if I'm talking about gradient, I must remember that m is equal to y2 minus y1 all over x2 minus x1. And that, how we're going to do that is we need to find 2 points on the gradient or slope. And if I have those 2 points, I'll be able to work out the gradient, because that's a possible question that they can ask in exams. The y-intercept equals initial velocity. We call this v subscript I, means v initial or initial velocity. When the two curves coincide, the two objects have the same velocity. We spoke about that in the previous one. Straight lines, uniform acceleration. Curved lines, non-uniform. So if I'm looking at the graph and I'm going like this, I know that it's a uniform acceleration. If I have a graph and my graph does that, I know that I have a non-uniform acceleration, right? If it has a constant acceleration, it is a straight line. Average acceleration is the slope of the straight line connecting the endpoints of a curve. So if I want to check, for example, from point here to here, I can find the average acceleration during that moment. Remember instantaneous acceleration? I can do this, and that will give me instantaneously what was my acceleration at that moment. In positive slopes, increase in velocity. We spoke about that. Negative slopes is increase in velocity, but in the negative direction. So it technically means you slowing down. Zero slope means motion with constant velocity. If it's on the x-axis, it means it has stopped. So that's important. And the area under the curve equals the change in displacement, which we looked at now. You need to know all your area formulas for triangles and squares and rectangles and so on. And that brings us to the end of the velocity time graph. And this all this motion is looking at is when it's usually looking at situations when you're driving somewhere, you're going somewhere. So the first one, the distance one, we looked at the man that was walking. In this one, we're looking at what happens when you leave your home and you want to go somewhere. What's your speed and your acceleration looking like? What are you doing on the road? You can use this graph to describe your motion. So 2 things you need to know: how to draw the graph. You need to also interpret from the graph. And you can see when we did this area calculation, how we did that. The next question you're going to be looking at is you're going to be looking at the acceleration time graph. Right, the next little thing we're looking at here is acceleration versus time. So I know that acceleration is measured in meters per second squared, and time is measured in seconds. So please make sure you get that. I also know that acceleration is defined as the change in velocity over the change in time, which when we mean by change in velocity, we mean v final minus v initial all over delta t, which we've looked at already. So what you'll understand about the acceleration time graph, of all the graphs, it's the most difficult one to understand, because the first thing here that you need to understand is that acceleration is an abstract concept, and now we're trying to draw a graph. So when we're looking at this graph, let's say I had to look at like I'm seeing here in this diagram, I want to know how fast an apple falls. So I need to do some sort of graph or an idea of how the acceleration versus time graph works. I want to know in terms of this falling apple or whatever the case is. So with this falling apple, I know that gravity plays a big role in falling objects, right? Now, when objects fall to the earth, we say they are accelerating at a constant value. And that constant value, we call that gravitational acceleration. And that happens at a value of 9.8 meters per second. And it will always be 9.8 meters per second if I have something that is falling. So I'm just giving you some additional information. All right, so in this situation, if something falls, right, if it falls down, because down is a natural thing for things to fall. You jump off a chair, you're going to fall down. Jump off a building, you're going to fall down. All right, we're going to take anything that moves down as positive acceleration, and anything that moves upwards is going to have a negative acceleration. All right, so let's first understand the different types of slopes. Right, with the acceleration time graph, there are two types of slopes, right? So in terms of your slopes or your gradients, they can either do one of three things. The first type of gradient that you're going to get is what we call a flat gradient. Now that flat gradient can either be on the, let's draw this up, positive y-axis, or it can be on the negative y-axis. All right, if it's flat, it means that you have a constant acceleration. And let's say, for example, it was 2 meters per second squared. That means you constantly going 2 meters per second, 4 meters per second, and so on and so on and so on. You keep going. Right? The second thing we look at is the other two types of gradients that you may get. The first kind of gradient that you may get will look like this. The other kind of gradient may look like that. So this one that's going up here, that's a positive acceleration. You're speeding up in the direction of motion. This one is a negative acceleration, means you're slowing down. And it also means you're going in the opposite direction of motion. Think about it. If you're driving your little vehicle, you're going and you're going and you're going and you're going, and eventually you come to a wall here, and you need to now slow down. So you might be going this way, but your brakes are telling you to go that way. So when you slow down, you're basically going in the opposite direction. So when we look at these kinds of graphs, your gradient's looking at the types of acceleration. So your gradient looks at acceleration. What we actually need to be focused on is the area under the graph. All right. Let's have a look at how that's going to go. So with these types of graphs, if I want to use these types of graphs to describe motion, I could be looking at a situation where, let's say I have this dog over here. This is my dog, and my dog's name is Spot. And we're going to take Spot to the park, and we're going to throw a ball. And we want to describe this motion. So what can this graph tell me about the dog's motion? So the graph at the moment is an acceleration versus time graph. So here we have acceleration in meters per second. that. These are my axes, and at the bottom here I have time in seconds. Right, so there's my dog Spot over there, and Spot's being given a ball, and we're looking at the acceleration. So it says here that Spot has it has a constant velocity of, I'm gonna use a blue pen, 2 meters per second. Oops. For the first 4 seconds. So we're looking over here. Right. Alright, so that's just the acceleration for Spot for that time. Then what happens is, from that time, the acceleration starts to drop. See, it starts dropping until at 6 seconds here it reaches 0, and then from there it keeps going. The acceleration becomes negative at 9 seconds. So, right, if she's speeding up or she's slowing down, then what can we figure out from this type of a graph? So we can look at a few things, because we know that acceleration, let's write this down, acceleration is related to velocity, right? And we know this because we know it's defined as acceleration, and as we spoke about this, we say that acceleration is equal to the change in velocity, delta V, all over the change in time. And that forms this little triangle that we can use, and we spoke about that. I've got A is equal to V over T. So the change in velocity over some time interval. So if I wanted the velocity, or how fast this puppy is moving, I can say that the change in velocity is actually equal to the acceleration multiplied by the change in time. Right, so that helps me a little bit, because if I'm looking here at this dog and I'm looking at what the dog's doing, I can look at the first 4 seconds. So if I look at the first 4 seconds, if I go from 0 to 4 seconds, that's from here to here, I can say that the dog has an acceleration of 2 meters per second squared. And we know that this whole thing happens in a time period of 4 seconds. So now I've got this is my formula, and I've got A, which is 2 meters per second squared multiplied by 4 seconds. And that's going to give me 8 meters per second. And that's going to be my change in velocity. Right? And what I'm going to get is a positive 8 meters per second. So it's the change in velocity for the first 4 seconds. It's 4 meters per second. So not just velocity, the change in velocity. Meaning that in that 4 seconds, that's how much the velocity has changed. But now the problem comes in, if I look at this, I want to figure out what happens to the velocity at the 6 seconds. So here's this situation. I want that now. But my problem is, if I look at it, over here it's 2 meters per second. But over there, it's 1 meters per second. And over here, it's 0 meters per second. So if you can see there is that the acceleration is changing over that line till the point 0, and it keeps changing. So how would I ever figure this out? I would have to plug in the values in that period of time, which is that 2 seconds between 6 and 4. But now that's too many values because I only have one formula. But we're in luck. If your formula allows us to say something that's really important, and the geometric aspect of these graphs is that's going to make our lives a little bit easier, is that let's look at what we're saying about this acceleration. All right, so what we looked at was we said that the acceleration, I'm just doing it in pink, in the y direction, it was going up by 2. And in the x direction, it was going across here by 4. Right, 2 and 4 units. So now I know that 2 multiplied by 4 is actually 8. And if I actually just look at what shape I've got here, I can see that I've got myself a rectangle. So when I'm looking at this type of graph, I know that if I can work out the area, it will give me so area equals velocity, or rather change in velocity. Oops. Right, which is going to give me that delta V. Right, then if I look here, where this point is from, let me just get another color. If I look here, I can say that area is equal to length times breadth. We know that formula. The length here was 4, the breadth here was 2, and 4 times 2 is 8 meters per second. And I get that same value. But now if I look at this other shape, let me just get another color. If I'm looking at this other shape, I've got myself a triangle. So can I see here? I've got myself a little triangle. And we figure out that the formula for a triangle is equal to half base times height. So if I can find that area of that triangle, it's going to give me that for that portion of the graph, from going at a constant velocity to a 0 velocity, I can use area of a triangle, which is then going to be equal to half times my base, which is from 4 to 6, so that's 2, times my height, which is up all the way up there, which is 2. So if I just want to look at that, I know my base is 2 seconds and my height is 2 meters per second squared, and I'm going to end up with 2 meters per second, which is my delta V, my change in velocity. So you might say, if I'm looking at delta T, right, it means that I'm looking at the base of the triangle. So when I want to look at these types of graphs, I need to be looking at the area, because that area of these types of graphs is going to give me the velocity at which it's working at. So when we work with an acceleration time graph, let's have a look here. When we work with acceleration time graphs, the area underneath the graph is going to give me the change in velocity. And I'm going to need that. That's going to be in meters per second. All right, so that's what that looks like. We're going to also find that with these graphs, the way in which they are structured is what we call a stepping graph. And when we talk about a stepping graph, we mean it looks like you're stepping. on a staircase. Alright, so this is an acceleration time graph. Let's just have a look at the information here. Right, the first thing we're looking at here is what is this? So if I'm looking here at the first one, it's a constant acceleration at 4 meters per second squared. Right? If I'm looking here on this basic line over here, this means that one of two things. If it's here and it looks like that, one of two things could be happening. The first thing that could be happening is that I have something that is, so when it's on the x-axis, it can be either something that is stationary or it is uniform motion. Right. If we just go back here, I just want to go back up here. Ooh, let's use green. Let's use orange. Alright. So this is going to give us the change in velocity that we're speaking about, right? What if I want the actual velocity? So what I can do is just move this out of my way. Right. I know that change in velocity actually means v final minus v initial. So if I want the actual velocity, or what we say instantaneous velocity, I need to do this calculation. So we can use this calculation to find the actual velocity. I'll get back to that other diagram now. Let's just have a look. In this one here, let's just take from t0 to t4 in that time period. Right. t0, right, is equal to my initial velocity. Right? And t4 in this situation is my final velocity. And delta v is my change in velocity. And I get that from sorting out the area. So what if the question asked you, what was Spot's speed? 1 second. What was Spot's speed at 4 meters per second? If at t0, so what was Spot's speed? At t4, if, so this is time at 4 seconds, right? If her speed was 1 meter per second at t0 when she started. All right, so in this situation, I have some information. I know that t0 is equal to 1 meters per second. They just gave me that now. I know about t4, I don't know that. But I do know this value here. And this value here is the change, we worked it out as the area over here. So I know that value, which is 8 meters per second. So all I need to do is substitute. I've got change in velocity is equal to Vf minus Vi, which is change in velocity is V of the T4 minus V of the T0. So this change in velocity is 8. The V of T4, I don't know, so I'm going to leave it as V of T4. It's a variable. Minus V of T0, which was 1 meter per second. This is meters per second squared. Sorry, I keep having to move this up and down. Just get it out of the way. Alright, so if I say VT4 is equal to 8 plus 1, it's going to equal to 9 meters per second. So at T4, Spot's speed was 9 meters per second in the direction of, I should put all of that in, motion. How do I know it's in the direction of motion? This value is a positive value. So when I work with these kinds of graphs, the best thing that we need to understand is that if I have this graph and I work out the area, it's going to give me the change in velocity. And if I have the change in velocity value and I have one other value, either V initial or V final, then I can work out the instantaneous velocity anywhere on this graph. So this is very, very important. You need to make sure that you memorize that, because there's no other way that you're going to learn how to draw or work out anything that's happening on these kinds of graphs. So let's say I had to look at something else, for example. Let's say I wanted the velocity at 6 seconds. All right. Velocity at 6 seconds. I know that so if I wanted that area, I know some information. I know that at T4, it's moving at positive 9 meters per second. And I worked out the area of this triangle as, 2 meters per second. So the change in velocity for that area is 2 meters per second. All right, and if I put it into the formula, I can say the change of velocity is equal to the V final minus the V initial. So if I'm looking here, I know that this is positive 2 is equal to the V final, so the V at 6, write that properly, the V at 6 minus the V at T4. So 2 is equal to V at 6 minus V at T4, which was 9. And if I take the 9 over, the velocity at 6 is then equal to 11 meters per second. Right, so that's that situation. So now I know the velocity here at 6 is equal to 11 meters per second. Right. Now, let's say I wanted to know what's the velocity of this whole situation. Let's pick a nice color. What's the velocity of this situation at T9? So I'm now looking at T9 and I want to know what is the velocity. Right, so there's two things I can do. I know that at T6, the velocity is 11 meters per second. But I need also the change in velocity. So the velocity at T6 is 11 meters per second, and I need change in velocity. The only way to get change in velocity is to work with area. So let's have a look at this triangle. Triangle goes there and there. Right, let's have a look here. Right, so area is equal to half base times height. The base in this situation is from 6 to 9 is 3. 3 seconds. But the height is different because the height goes from 0 and it goes along this y-axis at -3. So the height is now -3 meters per second squared. So let's put that into the formula. I've got A is equal to half times 3 times -3. And I'm going to get negative 4.5 meters per second. That's what we're going to end up with. And your answer has to be negative, because if I look at this graph, it has a deceleration. A deceleration means two things. Number one, spot is slowing down, right? It slows down. And it's going in the opposite direction. And if something goes in the opposite direction, it must have a negative value. So if you don't get a negative value, that means you've done something incorrect. All right, so I got that area. But I don't want, that's not my answer. I've got that. I want at T9. So I'm going to say the change in velocity is equal to the V at T9 minus the V at T6. My change in velocity is negative 4.5 meters per second. My velocity at T9, I don't know, minus my velocity at T6, which is 11 meters per second. So I've got now VT9 is equal to 6.5 meters per second. And that is spot's velocity at that point. All right, so that's how we do these types of calculations if I'm working with this kind of graph. Please make sure you have all of these notes, all of these calculations, that you understand what's going on. Please re-watch it if you don't know what happened. All right, so all we're saying is that if I want to use these kind of graphs, I can use acceleration time graphs to find velocity. How? I need to first find change in velocity. How do I find change in velocity? I need to use area. And if I have area, then I have a situation where I can work out an object's velocity, the dog's velocity, person's velocity, using this idea here. Right? So back to this graph situation over here. All right, so if I'm looking at this sort of setup, I've got here, from here to here, I've got a constant acceleration. From here to here, I've got a negative constant acceleration. Again here, positive acceleration. Over here, again, I've got a zero acceleration. So when you're working with, this is a positive, these kinds of graphs, you have a look, it looks like a stepping sort of situation. So if I'm looking here at the information, oops, just move this up here. I know on an acceleration time graph, the slope is meaningless, right? That means the slope doesn't give us, there's not enough info. The only thing the slope is telling us, it's talking about acceleration, how the acceleration is happening. Either it's constant, it's uniform, it's stationary, it's negative. That's all it's telling us. So one of these three things from here. All right, it tells us that, close this. The y-intercept equals the initial acceleration. So there's the initial acceleration up there. Then we said if the two curves coincide, they have the same acceleration. I'll show you something like that. If it's constant acceleration, it has a horizontal line. Look there. There's a horizontal line. Here's a horizontal line. It means constant. If there's a zero slope, this is the same thing. If it's a zero slope, it's a constant acceleration. And then the area, which is the zone here, and that there, and this here, underneath the graph, is going to give you change in velocity. And if we know the change in velocity, and we know the velocity at any point in time, then I can find the velocity. So I can find, so if I'm given, or if I know, say no rather, if I know I'm given, if I know or I'm given the velocity, the change in velocity, or the velocity at any point in time, I'm able to find the velocity at any other point in time. So make sure you have all of these notes. You've drawn the diagram, you've done the calculations for the acceleration time graph. All right, the next thing I've included is some summary points. I do think that it's NB that you get these graphs or these summaries. I've worked through these with you. This is just a better version of it. I would suggest that you take a screenshot and you sit and you get these drawings into your book so that it is there nice and neatly, right? It's looking at the distance. Let's just have a look here. It's looking at the three graphs. I've got the displacement versus time graph here. I've got the velocity versus time graph here, and I've got the acceleration versus time graph here. Right, the next part of the summary, this is also a very important one because this one just takes all the graphs and it gives you an overall view. So I know so I've got three graphs. Let me just divide this for you. Here's the purple line. Right, let's have a look here. I've got this one and this set over here. Okay. Right, how that is sorted out is that over here for the displacement versus time graph, if it's a stationary object, I must have a flat slope. If it's uniform motion, I must have a curve. I know that if it's going very, very fast, I must come close to the y-axis. If it's going very, very slow, I must move. So that's for fast. For slow, it must move closer. If I have a curve here, that tells me I have a constant acceleration. In the velocity versus time graphs, I have, if it's on the x-axis here, it means I have an acceleration which is equal to 0. If it's flat, I also have an acceleration equal to 0. And if it's up like this, I have a constant acceleration. And the last one here is the acceleration versus time graph. All right, and here, like I said, if it's on the line here, or if it's on the line, it means that it's not moving. All right, even here. Over here also, constant uniform motion on the x-axis. If it is a constant acceleration in the positive, right, direction, or in the negative direction, which means these graphs here are allowed to go into the negative area. All of these graphs, right? The distance versus time graph cannot go into, so no negative graph. Please get these graphs into your books. I've included two others. The next one looks like this, a little bit of a color one. It's summarizing everything, right? The more you look at these graphs, the more you draw them out and you write information, it sticks in your mind, right? It has to be done, right? I've done the same amount of work that you're putting into your books here. I'm doing the exact same thing. Here I've got the displacement versus time graph and the velocity versus time graph. And it shows you exactly what's going on. So if you had to do it in terms of vectors, that is how you would draw your vector diagrams out. These are the vectors. If you had to do it on a graph, these are what the graphs. So that's the graph of it, of the motion, and that's the vector. All right, so please make sure you take down these notes as well, NB, and that you take down both of these graphs with these notes. Read through it, go through it, see what's happening, see what every little curve looks at, look at what each line looks like. so that you can start resonating with you, because if you don't get it now, you're going to struggle in grade 12. So please make sure you sit, you pause, take down all of these notes, go through it, read over it. Obviously, when we get back to school, if you are having problems, I'll discuss with you, but you need to show me that you've done all of this before you say to me, ma'am, I don't understand. Because I'm going to come back to these graphs and I'm going to say, okay, what don't you understand? And if this is not in your book, that's going to be a problem. And the last graph looks like this. In the last graph, all they've done in this little summary as well, we've done it a little bit differently. What I've done here is I'm comparing two graphs. So you'll notice that you've got graph A in one color and graph B. And then here is the discussion at the bottom of what's happening in each graph. Remember what I spoke about, and I said in all of your notes, it says if the two graphs cross each other, they're doing the same thing at the same moment. This is what I meant by that. So if I'm looking here at graph B in the first one here, displacement versus time, I've got graph B, which starts with a curve and then it joins graph A. But graph A starts at a straight line and then it continues. So you need to understand what's happening with these graphs if you get two graphs on one piece of on one Cartesian plane. So this is the notes on intersection points. And I know we've talked about it, but this is a more detailed idea of what we mean by an intersection point. You need to make sure that you take down these graphs, take down the notes, pause the video so that you can get through it. I'll zoom in for you here. So this is your displacement time graph and all the information of those two graphs and what's happening with them. And then I'll look at graph B over here. I'll just zoom in enough for you to have a look at what's going on. So that's the last part of the graphs. All right, so please make sure you get all of the notes, everything into your books so that you are prepared for the next video, which is kinematics 4. And we're going to, instead of using graphs, we're going to use equations. So we're going to work with word problems, we're going to work with equations, we're going to do calculations. So that will be uploaded tomorrow. So for now, that's on Friday. Please make sure that this is done. Don't be lazy. And I'll see you guys in the next video.